What's up, everyone? Online prep coach Oscar here at prepcoach.com, back with another new seminar. And yes, it is very early in the morning, so if I had CPAP hair, that is why. Woke up, tons of work done, up at 2 a.m., feeling good, had some extra time, so I figured why not come down and record a seminar. Slu-Pp-332. So that's what we're gonna be talking about today. It is one of the coolest compounds out there. Been around for a while, and there's a lot to really understand and a lot to really unpack. So give everything a little brief backstory. So I first started using this in 2018. We started using it mainly to reverse like chronic kidney disease, so CKD, and some hepatomegaly, so people that have enlarged livers. And it worked extremely well. Then started realizing, ooh, over in the drug tested community, over in the Olympics, we started realizing that this was not on any banned substance list, which meant that it was completely legal to utilize. Implemented it, saw tons of changes to strength, to endurance, to lean muscle mass. Made it easier for individuals to make weight, everything. Like it was cool. It was awesome, positive after positive. Then started introducing it into the bodybuilding, powerlifting, strongman community. And it took a while to gain traction. There was one specific place online that first started selling it, Bio something. I give them a lot of credit because before them, there was literally just, you find the CAS number, you get it actually made, you have it synthesized, you get it, you mix it up yourself, you do your own thing. And that was very laborious for a lot of people. A lot of people had to pay a lot of money out of pocket to buy in certain quantities. And it was a very annoying process for a legal compound. Now though, 2024, coming up to 2025. By the time I release it, it's probably gonna be 2025. Now you can buy it everywhere. And it is such an awesome compound that I thought, yeah, probably time to talk about this. So with that, let's first look and let's backstep. We have a couple different things to talk about today. Yeah, we're gonna start off with where everything started off. So we're gonna scroll back even further. We're gonna look at a compound called GSK 4716. GSK 4716 modulated estrogen-related receptors of the beta and gamma variety. So what we're talking about with SLU is an overall estrogen-related receptor agonist, specifically alpha. That has a little more pressure on the alpha, still some beta and gamma. We'll talk about that in a second. So we saw that this was mainly modulating beta and gamma receptors. It's supposed to be like a Y for gamma, but I can't do that, so that's what you guys get. Mainly started operating on that, and they started realizing the muscle mass changes, the changes to health, the changes to all these things wasn't quite there because they didn't have the concurrent stimulation of that alpha receptor. So this came around in 2000. So this is very old research. This is very old technology. Estrogen-related receptors as a whole has been looked at for freaking ever. It's been a very long time. We're looking at these being structurally related to estrogen receptors, but obviously not because there's no real endogenous ligand that really binds to them. But at the same time, cholesterol is an agonist, and as you're gonna see, we'll talk about acetylation, sumylation, phosphorylation, everything. So we start off with this, right? Okay, 2000 happens. We realize, okay, we need to somehow modify this compound to get some alpha receptor stimulation. So what they did was super cool. They looked at it, and on that left structure, they looked at phenylalanine 328. They went over there. And what they did was they extended the aromatic process to allow for pi-pi stacking, which did what? Increased massively the actual efficiency and the targeted nature of that alpha estrogen-related receptor. It's cool. They originally, again, before they actually modified this compound, and by the way, then that gave us all of the SLUs, because there's more than just Slu-Pp-332. That's just kind of the most efficient and effective one in today's society. They went through the whole knockout mice process and saw that the mice without that actual estrogen-related receptor alpha didn't have negative health consequences, so it wasn't really pivotal for like life, but they also had the least amount of muscle mass. So you can go to the argument of frailty as you get older, you break, you fall, you break, you fall and hurt a hip, and all of a sudden then you have to go get a surgery done, you get an infection from that surgery, immune system's low, and then you die. So that's generally why people say as you get older, you need to maintain your muscle mass, because then it's those small micro injuries that can really end up causing problems. So not only that though, but then there are some other health cascades we're going to talk about in a second, but this is essentially what everything started off as. So even though I came into the party with SLU at 2018, this has been around since 2000. So it's very old technology. As we kind of scroll forward though, everything's gonna make a lot more sense as to the differences between these related receptors and why we're so happy that we can get some more alpha stimulation. But before that, we have to understand a little bit more about mitochondria, because if we don't understand mitochondria, being that this is a very big mitochondrial player, then we can't really understand its full capacity in action. So then we'll go to the estrogen-related receptors, and we're gonna literally cover everything in these seminars. And by the way, if I make stupid jokes and no one laughs at them, it's okay because I'm laughing. I absolutely love doing these seminars. I like that I could just set this up and just talk, and I don't have to say, oh, I gotta stop this at 20 minutes or 30 minutes. I'm just gonna go. So with that being said, let's look at mitochondria. So we're gonna try and make this a little bit bigger, trying to get better at these animations for you guys and trying to write a little bit bigger too. So I'm getting there. So this is not going to be anatomically correct, but it will make sense for the purpose of this video. So we have a couple different aspects of the mitochondria actually going on here, right? So first of all, over here, we have that actual outer membrane. That outer membrane has a high amount of permeability, so that phospholipid bilayer allows things to get in. We then have that intermembrane that has a high amount of what? Proton ions. Has to be there, right? And then we have the inner membrane, and this inner membrane is less permeable than that outer membrane. Still permeable, but less so. It is done this way because the mitochondrial membrane of mitochondria is, to me, I think one of the most important architectural parts, because if we have good things that can't come in, or if we have bad things that can't get out, that's all membrane mediated, all of a sudden we start running into problems. Clearance issues, inability to actually hit chemical thresholds, all these things occur. So I think those three areas are very important to understand. That we also have these invaginations coming in, right? Those invaginations are actually extensions of that inner mitochondrial membrane, so we can actually kind of do something like this, if that makes it a little bit better. So it's actually invaginations going in. This is called the actual cristae. Cristae, could be a good name for a kid, right? Cristae Kickle? Maybe not. Cristae are those invaginations coming in, and it's there to do what? Jack up surface area. This is super important because anyone who studies pharmacology, pharmacodynamics, pharmacokinetics, anything in the pharmacopoeia, chemical signaling-based world, you understand how important it is to have a greater surface area to improve the connection dynamics of any supplement, any drug, anything, or any chemical, any ligand. So that is there to literally increase surface area. Again, everything does multiple different things, but I try and focus on the primary, because if not, we'll be sitting here listing 20 different things. So we have those as the main areas, and then we also have one more, which is right here, okay? This is our actual matrix. In this mitochondrial matrix, we have two very important things to talk about. We have the actual mitochondrial DNA, so you'd see that as mtDNA, which is also maternal DNA, which is super cool. And then obviously you have DNA, you have to have your ribosomes. So you have creation, translation, basically. So that is probably the more important parts of your mitochondria, okay? We understand that. Now what we're gonna do is we're gonna actually zoom in a little bit further to really make sure we understand what's going on here. We're gonna basically cut this in half and see what's happening with different transporters and really how we're getting things inside to do actual genetic action. So if we have something, and again, I'll do this a little bit bigger. Okay, so we are going to have, and by the way, this is how I draw receptors. So receptor architecture, which is kind of how it looks like. Remember, everything I'm drawing is not anatomically correct. It is how I see things in my mind. So we have some channels, we have some receptors, essentially just trying to get things through these membranes, through these bilayers, and get them inside. So the reason why it's important to understand that those receptors are not even close to looking how they should is because it doesn't do justice to how cool receptors are. Does not matter what receptor you're looking at. It's all looking at magnetic and electrochemical gradient-based changes. So when we see receptor, whenever I do this in a video, that's the receptor. That's what I'm picturing in my head. We see ligand, hormone, binding and docking. Binding means it's gonna sit there and kind of tether and send chemical signals. It's not the lock-in key. There's nothing even close to that. That makes it, kind of dumbs it down and really doesn't give receptors how much love that they should have. So receptors are so freaking cool. They are absolutely amazing. And also one more thing, we have not said what? We have not said that mitochondria are the powerhouse of the cell, and we never will, because they do about 10 billion other more important things. Yes, they give energy, but that's like one of 10,000. So we're never gonna say that. We don't wanna say that. Anyway, going back to this. So this is basically zoomed into there. We have our receptors, we have our transport channels, we have all that kind of fun stuff. Over here, we're gonna have the nucleus of a cell, and we're in that nucleus of the cell, we're going to have DNA. That DNA spits out what? mRNA. That mRNA then what? Has to have some kind of an interaction with our ribosomes. Those ribosomes then give us an UFP, unfolded protein. So we're going to draw Mr. Unfolded Protein in a different color. I'll put blue there. We're going to draw Mr. Unfolded Protein there. Looks a little bit mad, right? Because he's unfolded. He wants to be folded. He wants to be able to go ahead and do action. So this unfolded protein will go ahead, and he's going to eventually have to go through this whole cascade in order to get into here. Now, what's important to remember is he doesn't just pass through there easily. No, it doesn't happen that way, right? What we end up seeing is some help, right? So first we have translocases. So memory-wise, it's super simple to remember. If we have Tom and Tim are both excited to go to the dance. They're excited to go to the ball. They're excited to go to dinner, whatever you want to call it there. But they also need what? They're young, they're underage, whatever. They need a chaperone to get there. So what we have is this unfolded protein going through that translocase of the outer membrane, having interactions with the chaperone protein cell, and then getting transported via the translocase of the inner membrane. So Tom and Tim need a chaperone, and that's how we're getting this unfolded protein now into the actual mitochondria. And now we can do, I think I'm screwing up my colors here. So now he's in there. He's going to have what? Some kind of an enzymatic interaction. So he's going to play around with some enzymes, and that is going to give us what? He's not mad anymore. He's happy, because why? He's folded. He is now folded or enzymatically activated, or there's tons of different terms you can use here. But essentially, that is what we're looking at in terms of the most important parts of our actual mitochondria. And then what's happening over here with DNA, mRNA, and getting unfolded proteins into the mitochondria to fold them and then have ultimate epigenetic actions, because now they can actually do real things, send real signals, cause real expressive based changes. Now, one thing we're going to scroll back and look at real quick is important to understand, because since we're talking about SLU, which is technically a mitochondrial based peptide, I don't even really like calling it that anymore, because it just does so much. I feel like it's one of the only peptides that kind of does it all, and it does everything pretty well with very minimal negative side effects, which again, we're gonna get to. If we scroll back to here, to the actual mitochondrial DNA, mtDNA, if we understand other peptides in this category, what is one that stands out when we think about mitochondrial DNA? We think back to those short open reading frames, right? Scroll back a little bit further, and what do we think of? Mitochondrial open reading frame of the 12th sRNA-C. So as we're talking about Slu-Pp-332, We're also remembering other peptides and other compounds and supplements that are going to be involved in this entire process. One of those is going to be MOTS, and that's more the mitochondrial DNA. So even though SLU and MOTS are two mitochondrial peptides, they're working via completely different cascades, and the route that a drug is traveling, the ultimate action that it has, changes its end fate. So there are things that MOTS does that SLU does not. There are things that SLU does that MOTS does not. That's how it is. That's how it's always going to be with every bit of supplement and pharmacology out there. Because if they did the same thing, then there would be no alteration to the chemical structure. There wouldn't be alterations to the name. There wouldn't be alterations to the end fate and to the entire cascade traveled. So because of that, we have different names, different structures. They do different things. Even if they're technically supposed to do the same thing, the same end fate, how they get there can change enzymatic, ribosomal processes along the way. So if you say like these are both mitochondrial drugs, that's like saying I live in a box. Like, no, I don't live in a box. Like technically the house is square, but like there's bathrooms, there's bedrooms, there's, you know, maybe a turd in the toilet that no one flushed. There's a fridge full of food. Like there's a lot of things than more just saying a box. So, okay, we know the basics of how SLU came into being. We understand the basics on overall mitochondria. I think now we should kind of start turning our heads a little bit closer to SLU, but we have to go through the entire estrogen-related receptor conversation first. Because if we don't really understand that, then again, it leaves you a little less informed, and then you're making the mistake of trying to use SLU and you should use MOTS or vice versa or whatever. So to me, more information is almost always better, because then it allows you to make more informed decisions. And if you ever have to troubleshoot anything, you can go back in your head and go, ooh, I'm having this positive, this negative side effect. What's causing it? Oh, this, because it does that. So to me, more knowledge and education is always the best, as long as you be unbiased in your application with it. Because sometimes we can overthink, right? So we're going to be looking at our estrogen-related receptors. They are termed an orphan class of receptors because there's no endogenous ligand. There's no ligand that really binds to them. The problem with saying that, though, is that we still get action, and we still have major agonists out there in the pharmaceutical world, and then also, like I said before, in the cholesterol-driven world. So cholesterol is a very big agonist here. This is important because if we look at cholesterol, the common dogma in today's society is statin you to death, crush your total lipids, and bring down apolipos as low as possible and total cholesterol as low as possible. There was a study, this was done in Japan, like 20 million people, so a couple people there, and they saw that there was more and more cardiac risk and more cardiac damage whenever cholesterol levels were sub 200. Obviously, you're 190, 180, okay, but their range over there was like 200 to 250. So to me, why not kind of split the difference and say low 200s is where we want to be? We look at the world of statin usage today and what's happening. There's more and more cardiac events, and there's more and more mortality, there's more and more health problems, even though statins are being pushed more than ever. So that's very important to understand how important cholesterol is in terms of, essentially maintaining cellular membrane integrity. We need that integrity to do everything, and this is just a prime example of cholesterol being a very big agonist and doing so many other things other than just looking at what's doing in the blood or with your heart. So we look at cholesterol as being a big agonist. If we look at the actual receptor first of all, because again, there's an alpha, there's a beta, there's a gamma. If we look at the architecture of it, because I think that's pretty important to understand first, and this is not going to look architecturally correct, again, we're looking at our amine group. We then have our screwing that up. We have our N-terminal, which actually has our A and B. We then have our DNA binding domain. We then have our flexible hinge region. And then we actually have our ligand binding domain. Amine, carboxylic acid. This is essentially what these receptors look like. The difference between alpha, beta, and gamma receptors is going to be differences in shape, structure, and ultimate end action. So they're all kind of roughly going to look like this, but one might have a smaller or bigger end terminal. There might be changes architecturally in the actual DNA binding domain, things like that. But if we look at this a little bit further, this end terminal, this is super important because, again, we said no ligand is binding to these estrogen-related receptors. But guess what can still happen? How do we even make a chemical change then if there's no ligand interaction in classifying this as an orphan receptor? Acetylation, summation, phosphorylation. So we have our acetylation processes, our phosphorylation processes, and our summation processes. So add an acetyl group, add sumo proteins, and alter the covalent bond with lysine, add phosphate groups. We can do all these things that'll alter the end fate of what this receptor is actually going to be able to do. But essentially, it's this N-terminal based action that's causing these estrogen-related receptors to actually work. Then we have, again, and this is where receptor architecture is interesting, and I think this is more so where people run into problems. Meaning, if someone is a hyper or hypo responder to certain compounds, mainly look to the receptor architecture. Even with the technology we have now, I don't think our technology is that good in terms of really finding, diagnosing, and fixing these problems. So let's say that someone takes SLU, because this is the example, because that's what we're talking about. And let's say that they just get a terrible response. Let's say they only get negative side effects, they get no positives. It could be that their N-terminal is truncated. It could be that instead of it being this size, maybe it's like that. There could be a problem with even the hinge portion, so that flexible connectivity portion, so that you're only getting a 3/4 of a chemical scent. There could be so many things. These are just basic things that could go wrong, very generically talked about. That receptor architecture is very, very in-depth stuff and super interesting. Problem is we can't really influence that yet. So we generically can influence that via trying to drive apoptosis of receptors rather. So what we would do is if there is a essential problem that we think is happening architecturally with the receptors, we can essentially flood the body and cause so much receptor activity. Body has to do something with those actual ligands. And so we would literally create new receptors and slowly kill off those old receptors. The problem with that is this is not ligand driven. It is acetylation, phosphorylation, and summation driven. So the androgen conversation is one where you can overwhelm the receptors via essentially flooding the system with androgens, tons of negative consequences with that as well, but you can essentially upregulate more androgen receptors in that variety because we're looking at overall muscle architecture and we're looking at androgen load governing that conversation. So it's not that we're fixing the broken, it's that we are getting rid of the broken, recycling them, making new good ones. Not the same thing here, but just some overall food for thought. So we have that, okay? Roughly how things are looking, right? Estrogen-related receptors, let's go back and let's look at the alpha, beta, and the gamma. So these are gonna splice down here. We have our alpha, we have our beta, we have our gamma. Now these are gonna be governed by their epigenetic fathers, we'll say. I guess that's a good term. Not really, but we're looking at we have all the different ESSRs. We have the alpha, we have the beta, and we have that gamma. Now, obviously, these receptors are going to be governed by these actual genetic coding areas. So we have this estrogen-related receptor, the genetic variety, that genome, alpha. We're looking at this specifically being the one that, and actually, it's really the alpha receptor that's more heavily studied and researched, which is cool. But if we're looking at these and just kind of breaking them apart, this has the actual highest amount of expression, whereas the gamma has more moderate amount of expression, and the beta has the lowest amount of expression. Furthermore than that, if we look at the actions that these genetic fathers are giving to the receptors, we're mainly seeing it in here being more cardiac, energetic, and more myological, so muscular in nature. Whereas in the beta-based world, that's more looking at cell proliferation and differentiation. So we're gonna say proliferation, differentiation. Then we have the gamma, And that's going to be more over in the mitochondria and the brain-based world. So you can understand why it's important to have stimulation of alpha, beta, and gamma receptors in this estrogen receptor related conversation. So we understand how it's looking, we understand how things are kind of, going about from a receptor standpoint and where potentials we have for increasing maybe muscular tissue, energetics as a whole, cardiac tissue, all those fun things. We know a lot about the receptor architecture, we know a lot about the mitochondria, we know a lot about where this drug came from. Let's look at the actual application process. So we're gonna go through geographic, and actually before we go through geography, I'm gonna scroll back one more time. There is a huge axis that exists here. And again, this is very important to understand because if someone's out there watching this, they're most likely not just taking SLU. They're most likely taking at least one or two or 20, 30, 40, 50 other things that are also stimulating similar cascades. And we want to understand that because you can see where you can potentiate things. So it's super interesting and super cool. We have there's a lot. Okay, so there is an entire peroxisome proliferator activated receptor, gamma coactivator 1 alpha, through SIRT1, through the adenosine monophosphate kinase, through our estrogen-related receptor axis. So all of these exist, all of these crosstalk and cross-communicate, and I say cross-pollinate because I think it sounds cool, it might not, but they all interact with each other. So one interesting thing is if we look at PGC1 alpha, for example, we'll use this as the example. Whenever you stimulate PGC1 alpha, what's it doing? It is increasing the actual expression of the alpha receptor. Remember, alpha receptor is going back to myological energetic cardiac tissue. But the cooler thing about that is it's also doing what? Forming an actual complex with estrogen-related receptors. So you have this PGC1 alpha, you have this estrogen-related receptor, you stimulate PGC1 alpha, and you see complex being formed. So you can stimulate PGC1 alpha through multiple different ways. One of them, if we just look at the actual fasting conversation, when we fast, we're going to stimulate peroxisome proliferator activator receptor gamma coactivator 1 alpha, which is then going to cause further potentiation, interactions, complexes, and expression of our alpha version of our estrogen-related receptor. So obviously, if we are doing some form of fasting, we can have some benefit. Let's go ahead and let's look at us being actually hypocaloric. So we're dieting, right? We are pulling down our calories, we're losing body fat, all this cool stuff's happening. When we're hypocaloric, what's that generally doing? We're seeing a pretty good modulation on that SIRT AMPK axis, which does what? Because crosstalk, cross-interaction intermingles and also stimulates PGC1 alpha, which then increases the mitochondrial actions in cardiac tissue. So this specifically, this first one we're looking, or this second one rather, we're looking more at cardiac interventions. This first one, we're looking at fasting, fat loss, lipolysis, things like that. Just different examples to get your mind thinking a little bit. This is going to go ahead and increase that cardiac mitochondrial density. It's going to increase cardiac overall strength and integrity. It's going to pull down on fibrotic tissue, things like that. It's all happening because of that additional change to those estrogen-related receptors of the alpha variety. So this is just two examples of how fasting, being hypocaloric, and this entire axis works. Again, this axis then extends because if we have something like a metformin that also plays in that AMPK cascade, it'll also have direct interactions with the estrogen-related receptor. So all of these, if something does one of these, it will somehow find a way to, in some variety, cross-stimulate and crosstalk with the others. The problem is sometimes it doesn't have enough chemical strength, and so you might not notice the changes. Sometimes it's overwhelming, and then you see some massive positive or massive negatives. So again, just more food for thought. because there's a lot of things going on with SLU that, again, I just don't think it's given enough credit for, mainly because like it's not easy stuff. It's complex stuff, you know, and then we have those baseline understandings, right? We understand what's going on. Now I think the application is so important to understand, and it's so cool. This is where I feel like, coming from someone who's used it personally on clients, it's over 500 clients at this point since 2018. And by the way, I have all that data graphed and charted out. It's most likely going to be presented at a fairly big peptide conference in 2025, so that'll be cool. This is where the application really comes in, because on paper, reading books and research, that's 50% of the equation. The problem with understanding just pathways and how things should work is we don't know what's actually applicable and what happens in reality with real world athletes or dysfunctional or gen pop, because those are 3 different ways to metabolize compounds. And then we also don't know what is going to further play out with that other 50%. So we never have the full conversation, we never have the full idea, the full action, the full grasp on something, unless if you understand it and then apply it, and then you make your most informed decision. So now we're going with the geography of things, where things are interacting, what's changing. There's a lot of cool things going on here. So we're just literally gonna start listing some things. We'll go, make sure I'm still in frame. Yep, we're good. We're gonna go first with our stem cell interaction. So obviously everything is going to be having a mitochondrial component, because we talked about SLU being massively mitochondria dependent and has massive interactions with mitochondria. We know that. So in reality, what do we end up seeing happening? In the stem cell based world, we see a massive change in the upregulation in bone cell, or rather bone marrow derived and bone marrow release of stem cells. So that means we're increasing the actual proliferation and differentiation process of our stem cells. So remember, this is where we're looking at our CXCR4 STF1 cascade, where we have bone marrow, so we have hormone, or we have ligand rather, and receptor, that disassociation and pushing more stem cells into circulation of the bloodstream, that then you can either target where they want to go, or you can do a bunch of different things there. We're utilizing SLU in a specific therapy before we do our exogenous stem cell therapy, literally to get more action out of our exogenous stem cell therapy. So that's where I started off really understanding what happens with SLU in the stem cell conversation, because we were seeing drastically improved effects just by adding in some SLU before and also after actually having exogenous stem cell therapy. You can also just combine this with our actual endogenous players, like our stem regens and Phanazonium flossiquea and the different algae and aloe veras and all the cool things out there that will drive endogenous stem cell release. So that's a big one. Maybe we should list a couple of the examples first, and then I'll go through breaking them down. I think that might be a little bit better. We'll do myological, so some muscle. We'll look at adipocytes. We'll look at strength. We'll look at endurance. We will look at cardiac tissue. We'll look at renal tissue. We will look at hepatic tissue. We will look at the brain. We will look at ocular tissue. And I apologize if I'm taking so long to write these on the board. There's just a lot going on, right? And there's a little bug in here. I don't know if you saw that. We'll look at the inflammatory potentials it has. We'll look at the sexual dysfunction improvements we can make. Maybe we'll stop there. We'll see. But if we go down this list now, in the myological world, what's really cool about this is it's going to modulate glycolytic fiber type transformation on top of increasing intramuscular glycogen storage. So we have more glycolytic fibers, and we're going to store more intramuscular glycogen. So I think it's important to have that conversation Nothing in biology is black and white. You can't have mTOR without AMPK. You can't have anabolism without catabolism. You can't have a fully developed muscular architecture with only one kind of muscle fiber. Certain people can be dominant in one variety, but it's just like that light switch of turning AMPK and mTOR on and off. It's not really a light switch. Neither of them is either on or off completely. They're blunted. So in this world of the myological side of things, if you're a bodybuilder trying to use SLU to drive anabolism, it's going to do that via glycolytic means. So number one, if you are someone who's alactic dominant, what's going to end up happening is you run into ATP pool-based problems, which also blunts your alactic efforts with strength. So we'll talk about that in a second. But even furthermore than that is you're balancing those out, you replenish those ATP pools, you can now potentiate your strengths, increase the extra glycolytic fiber potential, and store more intramuscular glycogen. So if you look at the circumference of your muscle cells, of your actual muscle bellies rather, what is it? A lot of fluid, a lot of ions, a lot of glycogen, some nitrogen, some lipids. Like there's a lot of storage going on. If you were completely dehydrated and glycogen depleted, you would look terrible almost no matter who you are. So intramuscular glycogen storage is a really big part of the anabolism and hypertrophy conversation. So in the hypertrophy world, that's basically how we're utilizing it to improve our muscle size. Now in the adipocyte-based world, this one's super cool. This is the only compound out there, one of the only ones actually, that will drive up both lipolysis and beta oxidation in a parasympathetic environment. So the reason why that's so interesting, and let me write this on the board first and I'll start misspelling things. The reason why that's so important is because normally in the process of lipolysis, right? So we have an actual adipocyte, we have glycerol head, we have these fatty tails. We'll have our lipases being released, which will come in, cut those tails off. Glycerol head will get pushed out. Lipoic tails will get pushed out. The glycerol head will go off and maybe play with something else, go into the liver, and then we'll have those fatty acid tails going through the entire process through the mitochondria to ultimately be driven via beta oxidation, to ultimately be oxidized as carbon dioxide, to ultimately give us ATP energy. So the problem is that process of lipolysis is usually going to be more so stimulant driven, meaning we can get beta oxidation via just upregulating mitochondria, which is non-sympathetic for most. But usually if we're trying to drive that lipolytic side of things, that's where the caffeines or the ephedrins or other things like the yohimbines come into play, which there's nothing wrong with them, but they're stimulatory in nature. So if we are looking at when we should be sympathetic, we're looking at that, 2 to 4 hours a day whenever we're training. Other than that, you should be as parasympathetic as humanly possible. The whole goal is to be parasympathetic for about 20 hours out of your day. That doesn't mean heart rate's not going to go up and down a little bit, that's fine. But we're trying to be more calm and relaxed so we get better at utilizing body fat and utilizing stored energy for energy during those 20 hours of the day when we are not training. When we're sleeping, when we're chilling on the couch with our family, whenever we're working, things like that. So from the adipocyte fat loss conversation, Slu-Pp-332, because it's another SLU, really is one of the coolest additional players that can almost be in everyone's fat loss stack with almost zero negative side effects. We'll talk about those in a little bit though. Strength-wise, so we already hinted at this. So in this alactic-driven world, we're trying to maximally express strength. A lot of things involved. Some of the problems could be neurological, some of them could be leverage and mechanics based, but in this world, we're gonna look more so at the ATP pool side of things. If you are someone who is going ahead, and let's take a powerlifter, perfect example here, because I love SLU for powerlifters, strongmen, things like that, but powerlifters, you're gonna go out, you're gonna do 1 repetition max, right? You're gonna do your first attempt. Well, if you're so alactically dominant that you have very low glycolytic potential, that means you have low ability to recycle ATP pools. What happens with that is then you go out, you crush your opener, you do okay on your second attempt, and then third attempt, you bomb out. Because why? You were not able to recover ATP levels, ATP pools, in between going from your first to your last attempt. So it's very important to understand we want to potentiate our alactic fiber types by improving our glycolytic fiber types up here. So even though it's coming from the myological cascade, we are indirectly driving up our ability to recycle ATP pools, which is ultimately going to express more strength. Even cooler than that, whenever you are in between those one repetition maxes at a competition, what's that sound like? What are you reliant upon? that parasympathetic beta oxidative system. So this is also going to be fueling your recovery in between attempts. Pretty cool, right? I think it's cool. And that's also why in between events or at strongman competitions, any kind of strength and athletic event, what is the worst thing we could do? That's me getting jacked up. Me getting excited and jacked up all day. The entire meet day, the entire competition day. We want to be cool, calm as a cucumber, and then turn it on like an animal when it's time. And as soon as your event or your lift is done, turn it off. Start to recover. We want low arousal until it's time to be aroused. Or else then you're just bleeding through acetylcholine, burning through glucose, and you're gonna end up just running into problems and not fully expressing your maximal strength capacity. So now endurance, okay? This is completely what I think's going on. I don't believe this is found out there anywhere, but I started to apply SLU in the endurance world. So people doing different marathons. This was really where it started off over in the Olympics for me and some of the endurance-based categories of sports. And I was seeing people's breath holds improve like crazy. So in the endurance-based world, we have to remember the Bohr effect, right? So we're essentially looking at how we handle oxygen and carbon dioxide. Oxygen delivery to tissues is carbon dioxide dependent. So if you are having all the oxygenation in the world, but you're lacking in the carbon dioxide, the CO2 department, that oxygen is going to be useless. It's not going to get to working tissue. So as an endurance-based athlete, we are trying to literally improve how we handle carbon dioxide, to improve how we potentiate and utilize that oxygen, to manage lactate metabolism, to drive up mitochondrial biogenesis. The list goes on and on. So I started seeing our breath hold. So on the exhale, so hold on that breath hold. Spleen contracts, dumps erythropoietin and red blood cells out into the bloodstream. That's how we are improving hematological factors. That's how we're improving how we utilize our oxygen, because we're getting better at what? When you start like having that urge to breathe, that's because your body is trying to handle that carbon dioxide. So we're trying to improve. That's all carbon dioxide dependent. We're trying to improve how we handle carbon dioxide. So we put this in play, and all of a sudden we start realizing, ooh, okay, these endurance athletes now all of a sudden in the Olympics are able to hold their breath extra 20 seconds, literally in a matter of days on the breath hold, exhale. We then see the deep sea divers who were holding their breath hold maybe 3 minutes, 3.5 minutes, now at 4, 4.5, 5 minutes, seemingly over a matter of a couple weeks just with adding an SLU. So to me, I think this has to indicate an improvement to carbon dioxide management. Again, completely theory, but I think it obviously makes sense. It's improving how they actually handle CO2, which again, we talked about how CO2 and mitochondria, that proliferation effect, it's very, very close and very much kissing cousins, if you want to call it that. That phrase sounds kind of weird. Probably not going to say that one again. But CO2-wise, to me, it has to be that, on top of the glycolytic fibers, on top of the ATP pools, so many things. But to me, what sets it different in that endurance cascade, remember, this is all happening for everyone. All of these cascades are going to be happening for everyone at every single time. It's more how you epigenetically respond. So if you're training a certain way, it could influence which cascade it's going to be more apparent in. But it has to be carbon dioxide driven, at least from my mind. Now we go down the cardiac. So going back to this modulating cardiac inflammation, this modulating overall pulling off of oxidative load from the mitochondria in the heart, we are looking at this in terms of what it does in reality and what we see every time with heart failure-based patients, people with left ventricular hypertrophy, people with cardiac fibrosis, some septal-based, damage-based problems. We see it almost always. Oh, I smashed that little bug. I'm sorry, bug. We see it almost always increasing our ejection fraction rate, improving our ejection fraction rate, lowering if there's, like, we're going to say left ventricular hypertrophy, but I've seen it reduce right ventricular hypertrophies and things like that, and also doing a very good job of reducing fibrosis. The cool thing about that fibrotic cascade is it's also going to come into play over here in the sexual dysfunctional world. So remember that. So if you have any kind of cardiac damage-based event, SLU is probably going to benefit you. Renally, we see this time and time again, same thing, mitochondrial changes, reduction in inflammation, pulling off oxidative load. We see this time and time again, jacking up EGFRs, cystatin Cs, all that kind of good stuff. So remember, EGFRs are like the filter lining for our kidneys. So it's the filtration system. And if that is getting lower and lower, then it's causing more and more kidney renal-based damage. On top of that, then we go over to the hepatic world, because these are very, very close, not kissing cousins, because again, that sounds weird. But in the hepatic-based world, we see improvements to our traditional. So we're looking at our actual I'm gonna change this marker because it's dying on me. We are looking at our traditional changes too. So we're looking at the alanine aminotransferase and the aspartate aminotransferase. That is more of a marker of like liver-based protein unfolding, whereas the aspartate aminotransferase is more systemic protein unfolding. We're seeing improvements to those, and if there is a downregulation or upregulation or some kind of, we'll say, dysfunction is rather a better word for alk-phos, maybe some bilirubin problems as well, we tend to see that also be improved. Blue marker's dying, I'm gonna go with red. So now we carry on into the brain-based world. This is where we can utilize SLU for a couple different things as a nootropic, as a neuroinflammatory modulator. We see it doing a lot of awesome things. Again, mitochondria driven and a couple other, I guess we'll say modulative cascades, very similar to with CO2, meaning a lot of this I have not found out there in the research, but I've seen, and I've been able, maybe I'll talk about this before I write it down. I had some initial inklings that we were getting a nootropic-based effect. So nootropic has to mean that it's an antioxidant capacity, meaning in some variety it manages reactive oxygen species in neurological tissue. So okay, we get that. So SLU can technically be an actual nootropic if it's used properly. But then furthermore than that, I had individuals who needed dopamine replacement therapy with something like a dopamine reuptake inhibitor or some kind of dopaminergic driver. We were able to replace that product or cut it in half with a low dose of SLU. We had people on SSRIs that, again, we're at a higher dose of like a Wellbutrin. There are tons of things out there. Higher dose SSRI or moderate dose SSRI, we're going to cut that in half, or if not, take it completely out and replace it, or make up the difference with SLU. So all of a sudden, we look at that dopaminergic serotonergic relationship with the prefrontal cortex, helping to make decisions and all that kind of fun stuff. Because remember, we're going from lizard brain to the actual limbic system to the prefrontal cortex as we're processing emotions and then actually acting upon them. I believe that this has to have some kind of modulatory action, mainly on dopamine and serotonin, but I'm gonna say neurotransmitters. Like as an overall neurotransmitter aid, I feel like this is really being a good modulator because it has the ability to upregulate or downregulate your neurochemistry based on what you need. Because if you change dopamine, you change serotonin. If you change GABA, you change glutamate. You change MDA receptors. There's always these axes that exist. So to me, we can't say that it is a dopamine reuptake inhibitor or a selective serotonin reuptake inhibitor. To me, it's more of a modulator because we don't know what else to call it. But we've seen time and time again with dozens of people implement it and be able to improve their neurochemistry. So that also will mean that the downstream effects from that is that we see an actual reduction in neural inflammation. We see a positive driver on overall neural recovery. I've utilized this with a couple different players in the professional sports world. Q collars around the neck, which puts a little bit of compression on your carotid artery, push a little more blood into the brain. We'll add an SLU with that, and we see massive changes on actual scans to neural inflammation, overall neural damage fairly quickly. So there's a lot of things going on here, but again, half of the stuff I'm talking about here is literally just what I found over the years and me trying to connect the dots biologically. We know it works in reality, which is the most important thing to me. Now we're trying to explain it. And now that it's becoming more accessible to people, we should have more people doing videos like this and saying, hey, this was my experience. Oh, I found this bit of research, and we can slowly build this big library of why SLU is so cool. Ocular tissue. There's a lot. So SLU is one of the ways that I was able to reverse myself and my dependency on glasses. The biggest players for me I've talked about beforehand were some specifically made eye drops, some eye drills, but I know a big player in there because I saw a massive uptick and upregulation in my sight and the clarity whenever I started utilizing SLU. Before I utilized it on myself, this was going back to the Olympic-based world, utilizing it on archers, and then over in the NFL-based world with quarterbacks. And what we saw time and time again, we were taking it for other purposes, and what we found was an improvement in clarity. So the actual clarity of how you saw things was improved. Could be a cone rod thing, could be an actual optical nerve thing, could be the stimulation from the neurological tissue, could be so many things, but clarity improved almost every single time. What it could also be, and this is why it gets tough, is because as this is improving all these cascades and effects, we're improving how we utilize glycogen, we're improving how we utilize water, splash all over my face when I drank it. We're improving how we utilize everything, every nutrient in circulation. If you have a really big cheat meal refeed day and you just ate too much, usually the next day, if you do an eye chart, your vision will be worse because of how the glucose is being handled. You then also have the DHT, the dopamine, the estrogenic, because remember, this is estrogen-related receptor agonist. There's estrogen action, alpha-wise, in the eyes, not related receptors, actual estrogen receptors in the eyes. So in that ocular tissue, it's influenced by so many things. Not sure what it is, but it has to be one of those where SLU is driving up overall ocular clarity. Now, inflammatory. This is where it's interesting. So on paper, it should do all of these clear across the board. It doesn't always do this for everyone, but we tend, the majority of people tend to see modulations in things like interleukin-6. We tend to see modulations in TNF alpha. We tend to see overall improvements to inflammatory factors like our HS-CRPs. Not everyone, but certain people. I had a couple people where I thought we had run into tanking interleukin-6, because interleukin-6 is not good nor bad. It's like everything else needs to be balanced in biology. And we had thought that that was the problem, which turned out not to be his problem, but other people did have that problem, where SLU did tank interleukin-6 because they were taking, what was it? A milligram, 2 milligrams, 3 milligrams of SLU. It was pretty high doses. So, going on, sexual dysfunction. Changes, male and female. In the male world, we see an improvement to overall erectile tissue hemodynamics, and then the decrease in fibrotic tissue. That's for males. For females, we see an epigenetic expressional change in clitoral sensitivity. We call it this because once we stop utilizing SLU, the sensitivity changes tend to stick around for weeks, months, and sometimes have not died off yet. So this changes the epigenetic expression of genital sensitivity for our females. This started off, the male side of things started off in the PFS community years back, and then the female community, that was more so for the OnlyFans, the female adult actresses and things like that, to where the way it happens in the adult industry is they tend to have seasons. So it's like they will have all their scenes in 6 weeks, 8 weeks, 12 weeks, and then they'll have some time off, recovery time, literally. And sometimes there can be a downregulation in their overall ability to arouse and their overall ability to sense things, because there's just literally so much overuse of that tissue. And that can then throw off the scene. If someone doesn't seem as into it, then their job performance goes down. It's just all bad all around. So that's usually a good way during their actual seasons to supplement with some SLU. So there is a lot going on here. There's more. SLU literally does it all in some variety and fashion. Actually, no, we're going to stop, because there's a lot more we could talk about. We're going to stop there. We're going to talk about the negatives and then how to actually apply it, because there's a lot of things to talk about there. Now, I'm not sure, because I just do a bad job of following people, but I'm not sure who's talking about the negatives, but there's only a couple, and it does not happen to the vast majority. But it does not matter, because if you are one of those people that you get the negatives, you have to know that there is a potential for it, because at the end of the day, everyone responds differently. Anything can happen to anyone in any way when we're dealing with supplementation or pharmacology, especially something of this variety whenever we are like literally still discovering it. So whether this happens to one person or 20 people, it doesn't happen to 10,000 people, that's still people. People are still having these negative consequences. One of the things is we are seeing negative side effect profile-wise is an increase in gynecomastia. So technically, architecturally, similar to estrogen receptors, even though it's an estrogen-related receptor agonist. But like we talked about with that PGC1 alpha, like we talked about with that adenosine monophosphate kinase, like we talked about with all those axes and cascades, how they crosstalk and cross-interact, there is a crosstalk and potential cross-interaction with estrogen-related receptors and estrogen receptors. That has to be, again, not proven in research, but we've seen gynecomastia happen to some people. There has to be cross-stimulation of those estrogen receptors to cause gynecomastia. So that's one. Another one is an increase in tachycardia. Didn't want to spell out the whole thing, honestly. Increase in tachycardic events, so heart rate actually picking up. This should not happen, because SLU operates in a non-stimulatory capacity. The problem is if it's increasing the stroke volume, so how hard you're basically pumping that blood, how that heart's working, it has the potential to then indirectly increase your heart rate. It also has the neurological input. So if we're seeing an overabundance of maybe dopamine, or maybe we're seeing imbalance that's caused by this drug in someone who's not metabolizing it well, because everyone metabolizes this differently, then we could see an increase in tachycardia, because that's just increase in neural input. So cardiac-wise, there's a lot of different voltages going on. There's neural input. There's so many things affecting heart rate. Not really sure which one, but we know for sure that gynecomastia can be a thing. We know for sure tachycardia can be a thing. Another one, and no one's talking about this. I've been talking about this for years, and I want to put it in here so that everyone's a little more understanding of the potentials. Reactive oxygen species. This goes for every single mitochondrial peptide and supplement out there. Supplement-wise, though, you're more safe because you can only hit that physiological limit. You can't go above into super physiological levels. Once you go with peptides or hormones or anything in that pharmaceutical world, that's whenever we start to see problems at the mitochondrial level. So even though these are helping our mitochondria to either, because certain things like urolithin A will recycle damaged mitochondria. Certain things like SLU can drive proliferation differentiation of mitochondria. What ends up happening is as you are creating, first of all, getting rid of damaged mitochondria, creating new ones, you're changing the spin. So again, that water keeps hitting me in the face. We are actually modulating the spin of the ATPase involved. So remember ATPase, we're looking at hydrogen and oxygen being thrown off. What happens is as we're increasing the spin, that's what's allowing it to generate more ATP. So if you can imagine, again, going back to our mitochondrial picture, we're going to zoom in and we're just going to say that this is our ATPase. Yeah, that looks good enough. I'm going to actually write it out a little bit more clearly because I made this a little bit small. There we go. So that's our ATPase. So as it's actually generating and pushing back through and giving us actual ATP, what's it doing in the process? Throwing off our hydrogen, throwing off our oxygen, and also, because of that, then throwing off some reactive oxygen species in order to get us ATP. This happens in every mitochondria at every second of every day. To generate energy, you have to then literally throw off some form of we'll say oxidative damage, but that sounds really bad. To create energy, there has to be this process. Like we talked about with AMPK and mTOR, like we talked about with anabolism, catabolism, there's always this balancing out process. So to give, you have to kind of take away in a certain sense. The problem is, if you are taking that ATPase, because it's all spin related, this goes back to the previous seminar, we talked about the quantum world, what's forcing these ATPase to spin. Do you really think it's oxygen? There's a lot more things going on there at the quantum level to cause this spinning of mitochondria at the ATPase-based level. But again, we won't go there. So you're spinning, you're throwing off a good amount of ATP, good amount of ROS, and then you hyperspin it. And you spin it even faster because you're adding in MOTC and SLU and urolithin A and methylene blue. And it's just spinning harder and harder and harder. At a certain point, you will kind of cap out on the ATP side of things because there's only so much ATP you need, can generate, can utilize. And what's going to happen is you're going to get more and more ROS generation production. We see this whenever people take too many mitochondrial peptides, because what ends up happening is they start regressing and getting basic systemic fatigue resistance problems. So they start having the lethargy, the low energy, similar actually to whenever you overtake too much coffee, too much caffeine, where you just get too stimulated, you get too overly sympathetic. Same thing, different means to get there. But we're essentially looking at the same issue happening, and then people start getting sick all the time because if you are having all of these cascades driven so hard, you are never allowing yourself a time to get stressed out, so then you are never able to adapt as well. So even if you could handle all the ROS, the fact that SLU and these mitochondrial peptides drive so much healing, you're never able to have that stress response. Dr. Hans Selye, stress, adapt, stress, adapt, stress, adapt. That's how we progress as a species. And so we see this all the time in the literature with taking too many antioxidants, with taking too many this, too many that. We need to stress, and then we need to adapt from it. So I think those are the three main ones to talk about. They're very important, especially that last one with the ATPase spinning. Now, this is the application portion, which is pretty interesting because if anyone's ever watched any of this, any of my content beforehand, you'll know that I am very big on finding your own reference range. Same thing with dosages of any supplement, any compound, whatever. You're getting SLU through your medical provider, we are looking at going ahead and finding your reference range. I've done that since 2018, so my range is crazy with individuals. We are looking at the range, and I'm gonna make this pretty ridiculous, just to kind of really hit home the point. We have trialed everything from 10 micrograms all the way over to 2+ milligrams. Above that, if I don't have enough data and I have not worked with enough people on a certain topic or a certain dosage range, I tend to not talk about it because there's not enough there. N of 1's cool, N of 2's cool, but if you have 50 people or 100 people or 200 people, things make more sense. So those numbers are just, really not gonna be applicable. But what ends up happening is we're going back to chemical signaling. So remember, with SLU and with all pharmacology and supplementation, at least through my paradigm and my lens, I care less about peak plasma concentrations and I care less about half-lives. Peak plasma concentrations have to be there. Half-lives are gonna be there, but what we care more about is the non-genomic and genomic effect of drugs. So when we're looking at a drug like SLU, which is making mitochondrial genomics, so long-term changes, it's also gonna have non-genomic acute changes. So we are tending to look at what it's doing right now in picoseconds. As soon as you ingest an SLU capsule, something's happening. And 2 weeks, 2 years from now, you took that capsule, something is going to be affected by that. If it was chronically done, if it was only done one time, you make an epigenetic change the moment you take any supplement or any drug. That's just reality of taking things. That's why we have to be very careful and cautious. But 10 micrograms for dysfunctional, for Gen Pop, for athletes, basically nothing. Not enough chemical pressure. No matter what, we need enough chemical pressure to send enough of a chemical signal to tell our body to do something. If it's below a certain chemical threshold, which this SLU does obviously operate on, then there's just not enough in order to tell anything's happening. So as we work things up, we went to about, we'll say, 100 micrograms. And to me, for everyone out there, the minimum amount needed to stimulate enough and put enough chemical pressure is right about 100 micrograms to 200 micrograms. Below that, not getting enough action, can't really tell. Above that, situationally dependent, but almost everyone, the majority of people will get only positives, no negative side effects at 100 to 200 micrograms. Certain people still get tachycardic, some people still get gynecomastic, it just depends. But the mitochondrial ATPase overspin, it's kind of safe in that zone. So what I found over the ages too is look at the individual demographics of these people. Who has healthy mitochondria? Right? Athletes are generally healthier and have better functioning mitochondria, even if they are involved in polypharmacy, because they're exercising, they're getting outside, they're doing all that fun stuff. We then have people who has the worst mitochondria? Dysfunctional populations. That's why they're not able to recover. So generally, if we're looking at just a blanket statement of saying who's going to need more or less SLU, the sick will need more, athletics and athletes will need lower. Again, though, you have to create your own reference range. So we have that range. Then we kind of say, okay, what happens around the 400 to 600 microgram range? So we're going to say right around the 400 to 600 microgram range. So right in about, actually that doesn't. I'm saying this is more, lower end of the spectrum, higher end of the spectrum, because athletes can't take higher. That's what we're talking about. So at 400 to 600 micrograms, we tend to see a cap off. For athletes, usually with SLU at about 4-ish hundred. Some athletes will respond better to 600. It does depend on the demographic, but I think it also depends more on the individual. Utilizing it with bodybuilders, powerlifters, strongmen, basketball, football, MMA athletes. You go down the list of every athletics. I've had someone in almost every category utilize SLU. And to me, that's the sweet spot range where almost everyone gets all the positives, no negatives. And then a certain part, they won't even get any negative side effects. You just won't see any more additional chemical pressure. Or rather, you won't see any additional positives from the additional chemical pressure. So to me, maybe the range is like 100 to 400 micrograms. And in that 400 to 600 microgram range, maybe there's less, right? Whereas for the dysfunctional, so we're going to say that's athletics up there. The dysfunctional are generally going to be this one's not working. This sick population, the Gen Pop demographic, might need 400 micrograms plus because their mitochondria aren't as efficient. They're not also taking MOTS-C. They're not also getting sun exposure. They're not also eating properly. They're not also sleeping properly. So dosages will start to raise the more and more sick you get, but almost everyone caps out at about 1 milligram. And again, certain athletes will get amazing responses up to 1 milligram. Certain sick people will only need 100 micrograms. You have to create your own reference range. But to me, if we're looking at like the biggest range to work in, and make it simple, if you're a first-time utilizer going through a medical practitioner, tell them, hey, can we start with 100 micrograms and then every other week work up by 100 micrograms. And then once we see our performance or reasons why we're taking it start to decline, hold it there or pull back. So you go 100, 200, 3, 4, go all the way up to 1 milligram, and then go back through and take all your notes and say, okay, when did I respond the best? And then when did things stop happening? And then there's your reference range. Then you know where your dosage needs to be at based on what goal it is you're looking for. Above the 1 milligram to 2 milligram plus range, most people, some people did get better results, but the vast majority, I'm not even gonna put a number on it actually because I'll be wrong. The vast majority of people didn't see any additional benefits and then started having the problem with ROS, overproduction, and then started having problems downstream with just about everything else. So like we talked about, not being able to ever get stressed out, which means no adaptation. So to me, the range is, I mean, honestly, 100 micrograms to 1 milligram. Athletes will tend to be on the lower end of the spectrum in the couple hundreds. Sick people tend to be on the higher end of the spectrum in the couple hundred, 500, 600 plus range, but it will obviously, again, depend on the person, and it will depend on how bad your problems are. How bad is your need for mitochondrial A to what else is in place? So it's very situationally specific. Create your own reference range. I will also say that the delivery method is not a concern. Between all the traditional methods of delivery that you can give a peptide or pharmaceutical compound or supplement, not so much supplement, but we are looking at the oral preparation being just as effective as any other kind of method we can apply SLU with. We have trialed that over the years, and regardless, we kept coming back to the oral preparation. There's some cool potentials for technological changes in the capsulated versions of SLU coming out. That's gonna be super interesting, but that's a conversation for a different day. Oral SLU is the way to go. That's the rough reference range we're looking in. Find your own reference range and go from there. I hope that this can really serve as a cool springboard to start really putting SLU on the map, because so far, even though everyone loves it, it's so underappreciated. And that's just because it's still so new. Again, even though in reality it's been around forever, it's still so new, it's still hitting the scene, and it's still really just blowing up over the past year or two. So thank you guys so much for watching. Check out thepepcoach.com. See you guys next time.